Problem 55 states, the physics of circular motion sets an upper limit to the speed of human walking. If you need to go faster, your gait changes from a walk to a run. If you take a few steps and watch what's happening, you'll see that your body pivots in circular motion over your forward foot as you bring your rear foot forward to the next step. As you do so, the normal force of the ground on your foot decreases and your body tries to lift off from the ground. So for part A, with this information they want to know, a person's center of mass is very near the hips, at the top of the legs, and they want us to model a person as a particle of mass at the top of a leg length L. They want us to find an expression for the person's maximum walking speed, or velocity maximum. So, starting with part A, just gone ahead and drawn our little guy here. We've got his center of mass right above the hips, his leg length L, and to kind of draw that a little bit better, we've got our mass M at the center of the hips, his leg L, with a normal force going up from the bottom of his feet and force of gravity coming down from his body. So we know, since we're in circular motion, since our legs are moving in circular motion, we want to set our forces to our mass times velocity squared over L, and we can use this to find that maximum velocity. So starting off, we want to set our net forces equal to our mass times our gravity times the cosine of theta. And then, of course, that's going to equal the mv squared over L. And then to simplify that out, we can divide out our masses and then multiply out our L, and we're left with velocity squared equals the square root of the length of the leg times gravity times the cosine of theta. So yeah, take the square root of v, and I got a little bit stuck here because I didn't know how we would find the maximum velocity, but after digging around a little bit, I can find out that to find that maximum velocity, we want to set our function of cosine to its maximum, which is the cosine of 0 degrees, which is equal to 1. So we want to set that equal to 1, and therefore we can just throw that out, and then we get our velocity maximum is going to be the square root of the length of the leg times gravity. So that's our equation for part A. And then for part B, they want us to evaluate our expression for the maximum walking speed of a 70 kilogram person with a typical leg length of 70 centimeters. They want us to give our answer in both meters per second and miles per hour, and then comment based on your experience as to whether this is a reasonable result. Apparently the normal walking speed is about 3 miles per hour. So for part B, we want to take, well, I've written out the variables given to us. We've got our 70 kilograms, we've got our length of the leg at 70 centimeters, which I've converted to 0.7 meters. And we can just go ahead and plug that in. And actually the mass we know is, we won't need the mass because we canceled it out up here. So mass is irrelevant in this part of the equation. So we take our Vmax, we set it equal to the square root of that 0.7 meters times the force of gravity, and we're left with 2.62 meters per second for our maximum velocity. And then they want us to convert that from meters per second to miles per hour, which we can just use a little stoichiometry here, and then meters per second, 60 seconds per meter, 60 meters per hour, cross cancel all those, and we get 5.86 miles per hour. And considering the normal walking speed is about 3 miles per hour, it definitely makes sense that our maximum would be that 5.86 miles per hour. So yeah, this ties into what we're learning in class this week about uniform circular motion and forces of gravity and